So, welcome to all. This is a requested video. So, this I will cover because if the discussion is too long, so normally it will be boring to see. It will take more time. So, I thought that this topic I will cover within 3 or 4 lectures. So the topic we are going to discuss today, it is the safety features of PFBR to handle the transients. Basically, uh, I am from the construction and the um, design, so I may not able to give you the uh, insight vision of the operation point of view. Basically, I was involved with this. These are the things I did long back when under the guidance of Professor Chelapandi. Mainly, I was involved with numerical analysis, the computational fluid dynamics, the simulation, finite element modeling, mainly the analytical mathematics like uh, solving of system dynamics, uh, mainly the series solution of differential equation, boundary value problems, the linear transformations like Jordan canonical form to simplify the system dynamics uh, by keeping the eigenvalue same. So all these things I know much more in depth, but I think that is not required. So I'll just give a few ideas what I understand. I will share to you. So the transients. If you see somewhere in my channel, there will be some video on the transients of first spectrum reactor. That is all we know: ULOFA, UTOPA, and ULOHS. So this some details I already explained there, how it will occur and what will be its consequences. So to avoid or to handle such transient, what kind of design implementation or the features is incorporated in PFBR? In this lecture series, we are going to discuss that. So before starting, I used to tell everywhere, because this is my regular course when I used to teach in training school. You know, the our PFBR will be finally producing uh, 500 megawatt electricity, and my English, because I am from Calcutta, so my English may not be good, my pronunciation may be wrong, so I am excused for that. And the thermal power which will be producing through nuclear fission is around 1260 megawatt. It's a pool type, and there will be two primary loop and two secondary loop in the reactor, and four steam generators in each secondary loop will be connected, where the water Rankine cycle, and then it will go to the turbo generator to produce final electrical output of 6.9 kV. Then it will be step up in our uh, distribution or the generator transformer to 230 kV. Then from our substation it will be transmitted through the defined circuits. The temperature of the hot and the cold pool are 670 and 820 K. there will be two primary coolant pump on the top of the reactor, and there will be two secondary pumps in the loops. The level difference between the hot and the cold pool is around maintained 1.5 meter. Inner vessel basically separates the hot and the cold pool. Uh, the top of the reactor means the top of the empty volume of the sodium pool inside the reactors are blanketed using inert argon gas, and there will be around 1757 sub-assemblies. Among there will be 181 fuel sub-assembly. There are 9 plus 3 absorber rod driving mechanism. I handled basically from the scratch level some flask of this system. So I wrote the code and operated the system. This I written the code in. I developed the GUI, and the code I wrote in structured text. Uh, and the fuel will be mixed oxide with depleted uranium and 25% plutonium oxide. The 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 core component which will be in sodium pool. So those are D9 material. It's a titanium modified austenitic steel, and the other structures will be of SS316Ln. So as I was telling that before that, one video I will refer, that is also available uh, in my channel somewhere, that is the reactivity estimation, how the reactivity is getting estimated in the reactor, uh, which is called a five feedback mechanism. That also will be available somewhere in my channel. You can see that. So to handle the transient, the first and the foremost, I feel that important consideration we have opted, that is the negative reactivity coefficient. Okay, so in case of any abnormal increase in or in case of any occurrence of any transient, there is a ensured probability that the reactor will go towards shutdown. Okay, so the temperature and the power coefficient of reactivity are negative. In case of any abnormal increase in temperature or power, this will leads to reduction in reactivity, and this will occur recursively for power. Okay, only the expansion of coolant and the structural steel result in small positive reactivity. You know, this which is around 0.241 milli percentage per effective multiplication factor. You know, when there is a expansion of coolant and the structure or the geometry of the reactor, so definitely the uh, geometric buckling of the system, it will change, and basically uh, the entire thing is depend on the solution of diffusion equation as per the Fick's law. And if the geometry is altered, the coolant volume is changed, then the boundary conditions also it will be changed subsequently, and if you see the solution, that will change. So naturally the reactivity and all these things, there is a possibility to change, and which is positive. But this is compensated by the negative and prompt reactivity effects like Doppler. These are the things you can see in the in my that lecture where I explained the five feedback mechanism for reactivity estimation and the fuel expansion. So this Doppler, in case of Doppler, it is minus 1.32, and for fuel expansion it is minus 0.236. And main thing, when the transient will occur, if the raising time, when there is a shoot up, either overshoot or undershoot, if the I mean to say the gradient with respect to time, it is if it is sharp, then there is a this will create some problem. But here the entire time constant are designed such that it is time constants are larger, so it is in second. This is 50 to 100 seconds. So nothing will happen because you can tell there is no question of transient itself. It is almost it is steady state. Okay. The reactivity feedback resulting from the grid plate expansion and the spacer pad expansion of core subassemblies, that is also negative. It is point 869, and the differential rod, it is -1. So if you consider entire thing, if you consider overally, you can tell very well this is our reactor is when it will be operating, this will operate with a substantial negative reactivity coefficient. So this it is well capable to handle the transients. Now coming to the core monitoring, it is a very important parameter to control the reactor. The neutron detectors are provided for the protection against a transient overpower. In case of any abnormality, it will detect, and the system will respond, control system will respond accordingly. The sodium temperature, the monitoring of sodium temperature is done by providing three fast response thermocouples mounted on the central canal plug to the to monitor the central fuel subassembly sodium outlet temperature. There are two thermocouple each within a single thermoweller provided over the other fuel subassemblies to monitor the sodium outlet temperature from individual subassemblies. Okay. There are three thermocouples. Same, the response time is quite higher. I think it is thermocox, or yes, it may be thermocox make. Okay, these are provided in each of two primary coolant pump suction side to monitor the uh, reactor inlet temperature. Okay, and the flow delivered by the primary coolant pump is also measured, and the power to flow ratio is always monitored. This, in case of, that means how the enthalpy is evacuated through mass flow and all. The pump discharge head and the speeds are measured and used to use as a trip parameters for the protection against pump discharge pipe rupture, and if the pump is there is a seize or any other such abnormal conditions. The failure of fuel is detected by monitoring the cover gas fission product. Okay. And also the um, delayed neutron detector in the primary coolant in the sodium pool. Okay. Another important thing is clad rupture. Okay. So for that, there are two. You see, this is A1 and A2. These are two argon sampling port. Here you can see this one and this one. So there are the uh, argon samples are taken, that to monitor whether there is a clad rupture or not. This whatever this figure I have given here, it is long back, so more or less it will be same. There may be slight change. I'm not sure, but grossly you can consider those figures. Okay. So the clad rupture and the consequent ejection of radioactive material from the filled fuel pins are detected by cover gas monitoring system and the delayed neutron detector. Okay. This picture shows the position of all the sensors and the sampling ports. You see here this D1 to D8, this is the 8 delayed neutron detector modules, and there are 3 failed fuel localization module is there. You can see it is maybe 120-degree aperture is there. So around each FFLM can cover 66 exact figure. I think it will be given in some details in I given in the next slide. Okay. The number of delayed neutron detectors and their locations were optimized based on the detailed 3D transient CFD analysis. Okay, so based on that, where it will, which location it will be best to detect all these things are simulated. It's a 3D, very time consuming. You know that those area I was involved. So there, if you it's a exact 3D. If you take 1 to 1 scale, then you know the once it is after meshing, so there will be degree of very huge degree of freedoms, and your boundary conditions and should be very favorable to converge the solution. And sometimes you have to do some approximation. uh, Definitely that should be a fair approximation to converge the solution. Okay, so basically these are the this picture is showing the location of this argon sampling line to ensure the clad rupture, and the position of the delayed neutron detector, because that is a important foremost, I think, the neutronic sensor. It will be useful to predict the transient situation in the reactor, and also the 3 numbers of uh, failed fuel localization module. So this is the, you can see this is the one indicative representation of failed fuel localization modules, which are housed in the control flag. Okay, and each failed fuel localization module can take care of 66 fuel subassembly position. It's nothing but this is a mechanism. This is a mechanism to take the sample from the subassembly, uh, sodium, and detect the um, to detect the neutron. Okay, so this is the geometry of that. Here I have elaborated. So the sodium sampling sleeves the concentric over each thermocouple passage tube. There will be a, there will be a DC conduction pump to suck the sodium from there, and this neutron detector, it will be detecting the fission product, and it will locate the failed fuel location. Okay, so this is all about today's discussion. So I'll continue this discussion. I'll complete this safety feature implementation of PFBR to handle transients within 3 or 4 subsequent lectures. I don't know whether it will be useful or not, but somebody asked, so that's why I started this. Hope you gained something. Thank you so much. Thanks for your patience.